Welcome back. Now we're going to talk about Michael additions. Now, Michael, which you would think is someone's first name, turns out to be the last name of Arthur Michael. Also, another chemist from the old age. I think he definitely fancied the bow ties, as you can see here. All right, but Arthur thought about something interesting. What he basically said is, okay, we can make these enolates relatively easily with like keto compounds. And so what if we, instead of reacting them with your typical SN2 substrates, what if instead we start mixing them up with an enone, and then see what happens? Well, what he ended up finding out is that a reaction will definitely ensue in which the enolate that was formed, right, in this case from the diketo molecule, will attack specifically the beta position of the enone. And if you later on introduce a regular SN2 substrate like methyl iodide, the alpha position will be the one that will get alkylated. So you had kind of like a very regioselective way of performing this reaction. And the way that this kind of works out is as follows. You first deprotonate your diketone to prepare your enolate, right? And once again, here I'm just using hydroxide because the pKa of acetone is very low, much lower than water for sure. So you can prepare this enolate relatively easily. Now, if all you introduce is your enone derivative, now the idea right here is that if you think about a resonance structure of enones, you could basically move this pi bond over to the middle portion of the molecule and kick this pi bond set of electrons to the oxygen. This will leave you with a carbocation on the beta position, and it will leave you with a negatively charged oxo anion. But the point is that with that resonance structure, you will see that the beta position is the one that's the most electrophilic. So it becomes no surprise that when the enolate goes to reform its carbonyl bond and the pi bond of electrons goes out to attack, the attack happens at the beta position of your enone derivative. So then that will kick the electrons over to the next available carbon, and that will also kick the electrons of the carbonyl towards the oxygen. So you end up with this derivative shown right here. It's basically an enolate derivative. So right here you have a couple options. You could just introduce water and quench it and be done with it. Or you could do what I showed in the first slide, which is that you could introduce an alkyl halide to this intermediate. And the alkyl halide is basically just your typical enolate. So what this will do is simply reform the carbonyl bonds, and in doing so it will kick out the pi electrons of your alkene portion towards the methyl group of methyl iodide. The leaving group will take off, of course, but what that will entail is that now you have introduced the methyl carbon at the alpha position, whereas your original enolate was introduced at the beta position. So another way to think of it is that the beta position is electrophilic. It's waiting for electrons to come over, whereas the alpha position is nucleophilic. It's trying to go after things that want electrons, right? So you can basically um, introduce different functionalizations at both the alpha and the beta position, in just one go. So that's kind of nice. All right, now that kind of brings us to another reaction that is kind of like a follow-up on a Michael addition called the Robinson annulations, because in the Michael addition, as I've shown you already, we end up forming this ketone technically, right, at the end of the process, where we attack the beta position and then we use the alpha position for an alkylation. Now, when this happens, Robert Robinson kind of noticed that if you count around your carbons and you were to introduce more base into the system, what you would end up doing is end up generating a ring. And not just any ring, but a ring that happens to be an enone derivative. So the way that this ended up happening is that Robinson noticed that, okay, well, if you count, after you deprotonate this thing and you make your enolate, right? You make the enolate on that position. Um, you could count from the enolate down to the next available carbonyl to see, what will happen if this enolate were to attack that carbonyl. And in this case, this specific situation will give rise to a very small ring. And from the previous lecture, I mentioned to you, basically doing the Dickman reaction, that yeah, four-member rings aren't really not all that favored, so that this will not be exactly the course of attack. And you could also make the argument, well, between your aldehyde alpha proton and your diketo alpha proton, probably the alpha proton of the diketo is going to be more acidic anyway, right? So you can make that argument anyway. But even without that, the fact that this is a four-member ring is a no-go. So instead, deprotonating the alpha positions right here will be a little more important. So I'm going after the alpha position that's not being sandwiched, mostly because if we do remove that one and we go to the nearest carbonyl, we're also going to end up with a four-member ring, so that will not be constructive. But if this one happens and you form this enolate over here, although it's going to happen to a small extent initially, if you count from this carbon ion all the way to the aldehyde carbonyl, you'll find out that this covers a total of 6 positions, meaning that if this carbonyl attacks if this carbon ion attacks the aldehyde carbonyl, you'll end up with a 6-member ring. So, and that is definitely favored for cyclization reactions. So what you could do is say, all right, so let's go with that. Let's kind of highlight that 6-member chain. We know we're going to be attacking that. We know that the carbonyl one of the aldehyde is going to be broken and the electrons will move over to the oxygen. But we also now know that this will form a 6-member ring. So we could start by labeling the ring. So this could be position 1, and then for this sake, I'm just going clockwise around the ring. So from 1 through 6, right? And then we could say, all right, well, position 1, we're really not going to have anything else, but at position 2, we do have the carbonyl, so that's why I'm putting the carbonyl right there. At position 3, we have an acetyl group sticking out, so we will have that acetyl group sticking out at position 3. At position 4, there's nothing. Position 5, there's a methyl sticking out, so position 5 will have that methyl. And then at position 6, we're simply going to have the oxo that has been formed. So what happens now is that doing this in aqueous media with hydroxide, you'll have water around. So the alkoxy group is going to take a proton away from water, produce hydroxide in the process again, and now you have a beta hydroxy ketone in this case, right? All right, so what happens now is that with more heating, you end up coming back around and deprotonating this component. And then the electrons will move over to basically form the enolate out of this thing. So you'll basically reform an enolate. And if you look at this carefully, you might recognize it from the first lecture video of this series, that this is basically the first step in your typical E1CB reaction. You basically have the enolate getting formed, and then the enolate, once it decides to reform the carbonyl, the pi bond of electrons doesn't attack a different molecule. Instead, what it does is it moves over to the adjacent carbon and it kicks out the hydroxide, thus forming the enone. Basically the same thing that we saw in the aldol reactions in the very first lecture video. So this is how this whole thing happens, right? And I would really highlight and advise you to label all your carbons as you're trying to come up with a product of this thing, because otherwise you can kind of lose track of where things are. But that should help you out. And the last thing I'll say is that you might want to go backwards, right? Like you might have a targeted molecule that you're trying to get to. And what you want to see is in this molecule, especially if it's a ring structure, you want to see whether or not you have an enone. Because if you do, that's the first thing that you should be noticing, the fact that there's an enone within that ring structure. And then what you want to do is say, all right, well, now let's highlight that alkene bond within the enone. And one position away from that alkene, not towards the carbonyl, but towards the other side of the alkene, one position away, you want to highlight that bond as well, right? So it's kind of like across the street from the alkene, because this is going to be where the breaking of these molecules is supposed to happen, as far as you determining what original reactants you made this molecule from. Specifically, on the right side of the highlighted bonds, we are going to have an enone, right? And specifically, the alkene will be present on the carbon. It has to be adjacent, right, conjugated to the carbonyl, and that won't happen on the left side, because the left side you only have one carbon, right? And that's where the break happens. So the alkene has to be present over here for this to be an enone. And then the left side is simply going to just be the dicarbonyl, right? So then that double bond, you could literally just see, oh, that is going to be where the ketone used to reside. But that's how you might want to look at this thing, to be able to kind of make your way backwards, do your retrosynthesis as far as determining whether or not, this was in fact a Robinson annulation that you were carrying out, or Robinson annulation, not Robertson, it's Robinson, oops, the Robinson annulation that is actually happening. Okay, and with that said, I think we're finished with that topic. So in the next video, I'm going to talk to you about a few other derivatives of the Michael addition that you can carry out on enones. And at that point, we'll be done with this lecture. So see you in the next video. Bye-bye.